In this video, we present the solutions to homework number 1. In problem 9, we'd like to rewrite the values of x which solve both of these inequalities using interval notation. To do this, I find it's easiest to start by drawing a number line and labeling the values on the number line which show up in the inequalities. That is, labeling the value 0 and the value -1. Then it's simply a matter of shading the values which make this inequality true in red. Notice these values are all the values of x which are less than 0. And then shading the values which make this inequality true in blue. Notice these are all the values of x which are greater than -1. And notice the values which are overlapped in both red and blue are the values between -1 and 0. Since we want both of these to be true, we want the regions that's shaded with both red and blue, which leaves us the interval -1 to 0. The only question is, do we include -1 and do we include 0? Noticing here, since this is less than but not equal to, we do not include 0, giving us an open bracket on the 0. And since this is greater than or equal to, which includes -1, we want to use a square bracket on the -1 side of the interval. And we have our answer. Problem 10 is similar to problem 9. We're going to rewrite the inequality using interval notation. So once again, I'll start by drawing the number line and then labeling the important values on the number line. That is, I'll label -1 and I'll label 8, which comes from this -1 and this 8. Then using red, I will color the values greater than -1 because I want values greater than -1 to make this true. And in blue, I'll shade the regions less than 8 because I want the values of x which make this true. And now, since I have an and, I want the region that is both here and here, so that is the region that is both red and blue, which gives me the region between -1 and 8. The only question is, do I want to include -1 and do I want to include 8? Looking up here, I see that the x is greater than or equal to -1, which means I want to include -1, giving me a square bracket. While here I have x is less than 8, which does not include 8, so I have a round bracket. And I have my answer. For problem 23, we would like to state the domain of the function. That means what values of x are allowed to be plugged into this function. Noticing that this is a rational function, we have to assure that the denominator of the rational function does not equal 0. That means we need that x minus 1 times x minus 2 should not equal 0. So we simply have to find the values which make this 0 and exclude them from the domain. Well, x minus 1 times x minus 2 equals 0 when either x minus 1 equals 0 or x minus 2 equals 0. So we want to make sure that x minus 1 does not equal 0, and we want to make sure that x minus 2 does not equal 0. Well, that means that x cannot equal 1 and x cannot equal 2. Why is there an error in copying this damn object? In problem 24, we want to state the domain of the function f of t equals 1 over square root of t. In this function, we have two potential problems. Since it's a fraction, we want to make sure square root of t does not equal 0. But also, since we have a square root, we have to make sure the inside value of the square root does not equal a negative number. So we have to make sure that t is greater than 0, or greater than or equal to 0. So the t greater than or equal to 0 refers to the fact that we have a t underneath the radical sign, so it has to be positive. The t cannot equal 0. The square root of t cannot equal 0 refers to the fact that square root of t is in the denominator. So in order for square root of t to not equal 0, this means that t cannot equal 0. So we must make sure that t does not equal 0. And also we must make sure that t is greater than or equal to 0. So this means that t has to be strictly greater than 0. Because t has to be bigger than 0, but t cannot be 0, so t has to be strictly bigger than 0. And we have our solution. Number 25 is similar to number 24, except what we have in the denominator underneath the radical is a little bit more complicated. We need to make sure that the denominator of this entire fraction does not equal 0. That means we need to make sure that the square root of 3 minus x does not equal 0, and that 3 minus x is greater than or equal to 0. The fact that square root of 3 minus x can't be 0 is because it's in the denominator of a fraction, and the fact that 3 minus x has to be bigger than or equal to 0 is because it's inside of a radical. So that means that 3 minus x can't be 0, and 3 minus x needs to be bigger than or equal to 0. The fact that 3 minus x can't be equal to 0 is because if 3 minus x was 0, then we'd have a 0 inside the radical. So putting these two together, we have that 3 minus x must be bigger than and not equal to 0. That is, 3 minus x has to be strictly bigger than 0. Because it can't be 0 and it has to be bigger than or equal to 0, so that leaves this option. And this means that moving the x over to the other side by adding x to both sides, x is less than 3. And this is our answer. Once again, we want to find the domain of a function. Here we have a rational function, so we need to make sure the denominator does not equal 0. That is, we need to make sure that x times x plus 2 does not equal 0. Which means that x can't be 0, and x plus 2 can't be 0. So we have x does not equal 0, and x plus 2 does not equal 0. Or x does not equal minus 2. If x was minus 2, then x plus 2 would be 0. So we have two values which are unacceptable or are not allowed in the domain of this function. Specifically, x does not equal 0, and x does not equal negative 2. All other numbers are acceptable, and we have our domain. For problems 27 through 32, we need to decide if the following curves are functions. This boils down to the same process for each one. We're going to use the vertical line test. That is, we're going to draw vertical lines through every point of the curve, or at least an approximation of every point of the curve, and make sure it only hits the curve at most one time. In this case, it does, so this is a function. Moving on to number 28, we can start drawing lines. And immediately we notice any line that hits the curve also hits the curve in another place. So this is not a function. Let's take a look at number 29. This one is a little bit more complicated than the others, because many of the lines we draw that intersect the function intersected only once. But if we make sure to look at all possible places, we notice that this line, in fact, many lines in this area, will hit the function at multiple places. It only takes one line that intersects the function at multiple places to make this not a function. So 29 is not a function. So what we have so far is function, not a function, not a function. Let's go ahead and move on to number 30. You can probably guess already that this is not a function, but let's go ahead and draw some lines. Drawing vertical lines, things are looking good so far, but as soon as we pass this point, we start hitting the function multiple times. Notice this line hits the function at 2 places. So this line hits the curve at 2 places, so this is not a function. So we have not a function. Moving on to 31. And drawing our lines, we notice fairly quickly that this is not a function. So, once again, not a function. Taking a look at 32, we notice that as we draw our vertical lines, we only hit the function once. Notice if you draw a line along the dotted line here, you don't hit the function at all, but this value is not in the domain of the function. It's not a value you're allowed to plug into the function. So for every place you can plug a value into the function, you only hit the curve at most once, making it a function. So we have, for our last one, number 32, a function. For question 43, 44, and 45, we'll be using the graph f of t given here, which is the concentration of a chemical in the blood at time t hours. It's called the concentration function. So to answer 43, we simply want to know what y value, or output value, corresponds to the input value t equals 1. That is, what value y corresponds to t equals 1. So if we take t equals 1, moving up to where the function is, and to the left, we'll see that corresponds to 0.03. Or another way, looking here at the line coming up from 1, hitting the function and moving over, we see that 0.3 is the output, giving us an answer to 43 of 0.03. For question 44, we want to know what the value is of the time concentration function when t equals 6. This is almost the same as the last question, except it's asking you to put in 6 to the function instead of 1. So analyzing it like the last question, we see when 6 is plugged into the function, it gives us an output of 0.03. This is the same answer as the last problem. So we have 0.03 is the answer. And this is perfectly fine to have two outputs matching up with different inputs, or the same output matching up with two different inputs. For question 45, we're asked to find the value of f of 5. This is a notational way of saying plug 5 into the function f. So it's very similar to the last two problems. So we're going to look at what value comes out of the function when we plug in 5. So, drawing the line up from 5 and tracing it over, we see that the output is 0.04, giving us the answer of 0.04. For For question 46, we want to know at what value f of t attains its largest value. So what value do you plug into the function f of t to output the largest value possible? All we need to do to answer this question is look along the y value for the highest possible output. So tracing the function, we see that the function, or the graph of the function, reaches its highest point around this region here, which looks like our highest value should be somewhere around 0.05. Let's be more specific here. As we move this line up and down, we want to move it till it reaches the tip top of the function. And we notice that we reach the top of the function for the value 0.05 on the y. The next question is, what input value gives us the output value of 0.05, namely the maximum? Looking at the line coming down from the maximum value of the function, we see that 3 is the input value that will output the largest value of the function, 0.05. So our answer is 3. Or more specifically, t equals 3. Question 47 says, is the point 312 on the graph f of x equals x minus a half quantity times quantity x plus 2? This is asking whether if you plug in the value 3 to the function, do you get out the value 12? Specifically, it's saying, does 12 equal f of 3? Well, f of 3 is equal to 3 minus a half times 3 plus 2, which equals 6 halves times 5, or 3 times 5. Which equals 15. So the question is, does 12 equal f of 3? And f of 3 is 15. Since 12 does not equal 15, the answer is no. Next, we move on to section point 2, and we'll start by graphing some functions. Our first one is question number 5, which is the function f of x equals 2x plus 3. In order to graph this function, all we need to do is recognize that it's a linear function, and to graph any linear function, it suffices to graph 2 points on the function. It is easy to find points on a linear function. It's simply a matter of choosing an x value, plugging it in, and getting the corresponding y value. For this function, and for any linear function, one of the easiest points to find is the y-intercept, which is the point that has an x value of 0. So plugging in 0 into the function, we get 3. This is a particularly easy point to find because you can read it off the function when you're in slope-intercept form. There's the 3 that corresponds to the y-intercept. Next, we simply plug in any other point. I like the point 1 because it's easy to plug into this function, so we'll end up with minus 2 plus 3, which is 1. And we now have our second point on the function. So we have these 2 points on the function, and now it's time to plot them on a graph. Here I have plotted the 2 points on the graph. We have the point 1, 1 and the point 0, 3. Next, all we have to do is draw a line between the two. And now we have the graph of the function. Once again, for problem 7, we are graphing a linear function, so it suffices to find 2 points on the graph. Once again, I'll start with the y-intercept, which corresponds to the x value 0, and then the y value that matches with it, which will be 3. Once again, that's easy to read off, because if you plug in x equals 0, you get the 3. And we need one more point. So plugging in 1 to the function, I'll get the point that goes with it, which will be 1 times 9, which is 9, plus 3, which is 12. And we have our 2 points. Now all we need to do is place them on a graph paper. And here I have graphed the point 1, 12, and 0, 3, and I've drawn the line through them. For problem 33, we will be evaluating the function f of x equals x to the 100 at the value x equals minus 1. That means we want to find the output value when we plug in negative 1 and raise it to the 100th power. Now, raising things to powers is sometimes difficult. What we're doing is we're essentially multiplying negative 1 by itself 100 times. So we have negative 1, and we're going to be multiplying it by itself 100 times. And the important thing to realize here is that we have an even number of negative 1s. And if you ever have a negative 1 times a negative 1, they will match together and become 1. And since we have an even number of negative 1s, they all have a pair to match together, and so we multiply this together, they will all match together and become 1 times 1 times 1 multiple times, which will equal 1. So the key to making this problem simple is to realizing you have an even number of negative powers, so they will pair up and become all positives, and there will be all positive 1s, so they'll multiply to be 1. Next, we will evaluate the function f of x equals absolute value of x at the value x equals negative 0.25. I'm going to do this in two different ways because I think each is helpful in its own way. So what we're doing is we're looking at f of negative 2.5, which equals absolute value of negative 2.5. And the absolute value function is asking you how far away is this value from 0 on the number line. Specifically, if we have a number line, and here's 0, here's negative 2.5, and we're asking for this distance here. And the distance it is 2.5 units away. Distance is always positive, and the distance between these two values is 2.5. So, on one hand, this equals 2.5. Now I would like to look at this from a different point of view. Recall the definition of the absolute value function. The absolute value of a function is defined to be, or the absolute value function is defined to be x if x is greater than or equal to 0, and negative x if x is less than 0. This is just a fancy way of saying the absolute value of x should be itself if x is positive, and it should be negative of itself if x is negative. So looking at our value that we're evaluating the function at, negative 0.25. So checking which domain that's in, we notice that negative 2.5 is less than 0. So negative 2.5 lives to the left of 0, so when evaluating the absolute value of negative 2.5, we should be using this function on the bottom. So the absolute value of negative 2.5 should equal negative of negative 2.5, which equals 2.5. And we have our same answer looking at it from a different point of view. And that brings us to the end of homework number 1.